energy or the work unit. The reason why I say energy or work, because it depends on which textbooks you use. If you use a more recent textbook, then they'll tend to use energy. But if you end up going to an older textbook, they'll call it work. It's the same thing, right? Tomato, tomato, same thing. Also, the symbol is going to be identical, or not identical, similar as well. You can call it W for work, or you can call it E for energy. I typically use E for energy. And again, in chemistry, sometimes they'll call that W as well. All right. So, what is energy or what is work? Well, basically, it's how much force you use to move something. All right. So, in other words, if I actually take this calculator here and I put a pressure on it, but it doesn't move, I haven't done any work. Also, if I take the calculator and put it back, for example, again, I also didn't do any work because technically the calculator didn't really go anywhere. So the displacement has to not equal to 0 for there to be any work done. So here we go. Let's do the formula. The force times the displacement. Now I'm going to put a little dot because you're going to multiply these two vectors together. It's called a dot product, and you'll learn more about dot products in grade 12 vector calculus. But for now, you're just going to multiply the force times the displacement. All right, this is the real formula. And it's called a dot product, and you'll learn properly how to use it. All right, here's the real formula. Now, in grade 12, we modify this formula because a lot of you aren't able to take grade 12 physics in second semester at the same time as the vector calculus. So we need to help you to use this formula without knowing how to use the dot product. And so this here is a modified version of this formula, and you'll use this formula in grade 12 physics. Now, for you guys though, we haven't been doing a lot of angles, and this really doesn't make sense to you. So for grade 11, this is your formula. E is equal to F, the force, any force, times the displacement, all right? It's a regular multiplication, but there are some conditions attached to it, all right? And so here are the conditions. So this is your grade 11 physics formula, all right? And here are conditions. 1, you have to make sure that the force and the displacement are parallel to each other. That's the only condition for this to work. In grade 12, the force and the displacement could be on an angle, and it's okay, but we're not going to do any angles. And then here for the real formula, you can have a whole bunch of things like rotating, but they're definitely on different angles. But just for grade 12, in order to produce work, these two, the condition is that the force and the displacement must be parallel to each other. So force and displacement must be parallel. Okay, they can also be anti-parallel, and I'll give you examples that are forces that are parallel to each other. For example, let's do this marker here. I'm going to push it this way, and the displacement is also that way as well. So that's parallel. Okay. An example that is not parallel would be, for example, let's say you have a wagon and you are pulling it up here on an angle. That's FA, but the displacement, the wagon technically goes this way. That's your displacement. Therefore, there is an angle here, and you'll actually do this in grade 12. Okay, we're not going to do this in grade 11. We're going to assume that for grade 11 only, your applied force would actually be parallel. So that means instead of having a wagon like this and having the angle for the handle, you're going to actually pull it this way. This would be for grade 11 only. So this here would be parallel. Okay, so that's the condition that we're going to use this formula in. And everything that we're going to do and all the questions in the duotang actually does this condition for you. Okay, so let's actually define some more things here. E or W is equal to energy or the work, but I'm just going to use E for energy. All right, I'll write work as well. F is the force, and it could be the applied force like this, but it could be any force. Friction, tension, gravity, any force. So the force to produce work. And so anything could be even F net too. F net, FA, the friction, gravity, the normal, any of those forces, it depends on the question. So you have to read the question. And then the last thing is displacement. And you got to make sure that actually moves, because if it doesn't move, the displacement is 0. And so then that there's no work. You can also move it and put it back, but if the displacement is 0, which in this case, when you move it and put it back, it's also no work as well. Okay. Some of you wonder why that's the case. When displacement is equal to 0, there's no work. Well, let's say I lift weights. Okay, pretend the calculator is a weight, and the calculator is right there, and I'm going to lift it 10 times. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and I put it back. All right. How did you know if I did work? Well, you don't know unless you were watching. Okay. And so then if I said to someone, oh, I had a workout, and then they're kind of wondering, well, how do I know? Because nothing moved. And so that's the whole point in physics. You have to show evidence, and there's no time here. So the work in physics has to be basically displacement you got to move that calculator elsewhere. You can't put it back. All right. All right, let's do units on this. The units for these, the force is measured in newtons, okay? And displacement is measured in meters. So according to the formula, energy or work is technically a newton times a meter. But you know what? There's a dude called a joule that says, I'm going to make this the unit of energy, which is a joule. So basically, the unit of energy is J, capital J for joule. All right, you guys are ready for your first example since we've given you the formula for it. Here is a good example. You drag a 10-kilogram box across the ground at a constant velocity. So we'll draw my little 10-kilogram box here, and we're actually going to drag it across the ground at a constant velocity. So the acceleration is equal to 0. This takes you 294 joules of energy to do this. If the coefficient of kinetic friction is 0.2, so 0.2 is for kinetic friction because you're dragging it across, so it is moving. How far did you drag the box? All right, so if you thought you could ignore everything about forces, that's not true. You still need your free body diagram. So let's draw it. You have the applied force going this way. Let's say the box is going this way as well, the V, all right, constant velocity. We have friction pushing it back. We also have the normal force, and I'll do it in different colors. The normal force, that's your vertical, and then your gravity, which is your vertical as well. Okay, so this is my free body diagram. Let's plug in the formula here. Energy is equal to the applied force because we want to know how far we drag the box, and that's all we really have. So this is the formula we have right there. All right, so the applied force times the displacement. Do we know what the applied force is? Well, this is where you need to go back to your F-net equations. All right, so let's do that. Let's go back to our F-net equation. F-net is equal to ma, and that is equal to the applied minus the force of friction. Remember, it's at constant velocity, so the acceleration is 0. Fa is equal to mu k Fn. All right. Don't forget that Fn is equal to Fg, so we have Fa is equal to 0.2 times Fg, or mg, I should say. In this case, it will be 10 times 9.8, because remember, the blue vectors are equal to 0, or equal to each other, because the acceleration is 0 for that as well. Okay, so let's continue. Fa is now equal to 19.6 newtons. So you know the force applied is 19.6 because that's how much you applied against friction to get the box to move at constant velocity. All right, now that you know that, we can plug in and figure out how far you push this or drag this along. So this would be 294, 19.6, and the displacement. And so now we have the displacement calculated as 15 meters. And there you have it. All right, let's do another example. Another type of energy is called gravitational potential energy. What is this type of energy? This type of energy is the energy required you to lift an object, all right, any object to a height. It's to a certain height. At that height, the energy is stored there due to its position from the ground until it's released by falling. This energy is transferred into speed. So let's do an example here. Let's suppose that you have a table, okay, and you have a bowling ball. Okay, so here's the bowling ball, and it's very, very heavy. Typically, they're like, 9 kilograms or something. They're really heavy. Okay, or sorry, not 9 kilograms, more like 9 pounds, but still pretty heavy. So, what you're going to do is you're going to lift it. Now, when you lift it onto the table, here's your table, you lift it and put it on the table. You know that it's going to take you a lot of energy because this bowling ball is really, really heavy, and you're going to lift it onto the table. That takes a lot of energy. Okay. Once you lift it and place it on the table, that ball has energy stored because you use your muscle to put the ball there. And because it's positioned from the ground, that means that it is stored energy. Now, let's suppose somebody comes along, all right, another person comes along here, all right, and they have their foot right there. If the ball were to fall onto the foot, so let's say we give it a little push, it rolls and falls on the foot. Do you think that would hurt? Well, yes, because you put the energy there, and then when you release the energy, it's released by falling. And when it releases by falling, that energy you put in comes out as speed. So the energy is transferred into speed. And so therefore, it will hurt. And that's gravitational potential energy. All right, so what we're going to do now is we're going to calculate how much energy you need to actually lift the ball up, and then also how much energy will it hit your foot. So, the damage, all right, in terms of how much foot damage you'll get from that rolling ball. Okay, so let's calculate that. I'll do another example. Let's say we have a shelf. So here's a nice bookshelf. All right, and let's say you want to put a big box right on top of the bookshelf. This is your bookshelf, because some people like to store boxes on top of bookshelves. I don't know. Anyways, we're going to lift the box. lift the box. Okay, so we're going to lift the box, and this here's your ground. Let's say if we lift the box, we're going to use the least amount of energy. And when you do that, you're going to lift it at constant velocity. You don't want to like accelerate it. That takes too much energy, too much force. All right. So you want the lowest amount of force required. All right. So 1, the least amount of force. So the least amount of force to lift the box. In this case, A is going to equal to 0, right? Because that takes the least amount of force. If there's an acceleration, that's going to give you more force because F equals ma. All right, so this will give you the least amount of force to lift the box. So ma is equal to the force applied minus the gravity. Because remember, when you're lifting the box, if we did the force diagram, a free body diagram, this is FA because you're going to lift it, but you're also lifting it against gravity. And we're going to make sure the acceleration is 0. Okay, so if acceleration is 0 in that case, then that means the applied force is equal to gravity. So let's figure out the work done. The work done in this situation to lift the box up is going to be the energy is equal to the applied force times the distance or the displacement. In this case, this is going to be FA times the height, right? Because we have the height of the bookshelf. All right, so we have the height. So now we know that the energy required to lift something up is going to be equal to FA, which also equals to FG or mg times h. This here's the formula for gravitational potential energy, mgh. All right, so let's try this formula out. It's a pretty simple formula. Here's an example. How much energy is required to lift a 17 kilogram box up 8 meters high? Literally, you just plug it in. I like to put EG so you know that I'm thinking about gravitational potential energy. There's my formula. The mass of the box is 17, gravity is 9.8, and the height we're lifting to is 8 meters, and this here is the answer. 1,332 joules, 0.8 joules. And there you go. Last type of energy I'm going to talk about is kinetic energy. And then I'll do a quick summary of all the different type of energy at the end of the lesson. So the last one I'm going to talk about today is called kinetic energy, and that is the energy of movement. Energy of movement. That's essentially the energy required to accelerate an object, or in other words, to bring it to a certain speed. So remember that bowling ball, and it's going to drop on the person's foot? Well, that is now considered to be kinetic energy because it's moving, because it's energy of movement. But really, technically, it is the energy required to accelerate an object to a final velocity, whatever that velocity is. Okay, so now keep in mind when you're actually moving something, what actually moves the object? Is it FA? Well, if you're thinking FA, you're actually incorrect because don't forget some scenarios have friction. So the actual force that moves something is F net because it's FA minus FF to give you F net. So in this case, it'll be F net equals MA. So remember that F net causes the movement. All right, so keep that in mind. Causes the movement. All right, so let's actually work this out. So again, our energy is going to be F times displacement. So we always start with the original formula like I did with gravity as well. So we have F times D. And remember, we're doing kinetic energy, which actually the force responsible for that now is F net, not F applied, not friction. So F net times D. Now, F net is equal to MA, like so. I'm wondering, has anybody seen this part of the formula anywhere before? If some of you are thinking, I've seen that formula before, then yes, you are correct. It's this formula over here. V2 squared is equal to V1 squared plus 2AD. This is the formula, or this part of the formula you've seen before. What I'm going to do is I'm going to rearrange this, and then I'm going to sub that in. So it will look like this. AD is equal to a half V2 squared minus V1 squared. All right, so I just rearranged it to give me that. And I'm going to now replace this back right in there. Actually, technically this part. So here we go. M, a half, is V2 squared minus V1 squared. I'm going to bring the half out because usually all like coefficients go out in front. Okay, perfect. Ta-da! So this here is basically the kinetic energy formula. Now, a lot of the times we assume something. We always assume, well, not always, sometimes we assume that V1 is equal to 0. So it starts at rest. So if it starts at rest, then we can say that the kinetic energy of any object is equal to a half mv squared, where v here is the final velocity. All right, let's try this example. You accelerate a 10 kilogram box from rest with a force of friction of 20 newtons for 8 meters. Assuming there is no friction, what is the final velocity of the box? There's actually two ways to do this. And you'll notice that in this unit, you can do a lot of the questions the old-fashioned way using kinetics and dynamics, or you can use it just using energy. Technically, it's really easy. Well, easier using energy. So what I'm going to do is I'm going to divide the page in half, okay? And I'm going to show you how to do it the energy way first, and then I'm going to show you how you would have normally done it using kinematics and dynamics. So I'll do kinematics, dynamics here, the old-fashioned way, dynamics, and I'll use the new energy method over here. Okay. So let's actually do the, I guess we'll do the energy method first. Here we go. And then you'll notice how easy it is. You're going to accelerate the box from rest. And you're going to use the force of this for that distance. Basically, when you think of energy, you have to think of the energy before and what it's transferring to after. So for example, I put in my muscle energy before, and then I'm going to transfer that energy into, well, it gets transferred to a speed. So essentially, what's happening is I have my applied force. That's how much energy I have before, and it gets transferred into the speed of the box. And that's my formula. All right. Plug everything in. This here is 20. The displacement is 8. This is half. The box is 10. And I don't know my final velocity, but that's okay because that's what I'm trying to solve for. And there's my answer, 5.65 meters per second. And then I'm done. All right, so basically with these energy questions, it's usually one type of energy being transferred to another type of energy, or you're conserving energy. Basically, all the types of energy here will equal to all the other types of energy over there. All right, now let's try it with dynamics, the old-fashioned way. With dynamics, you need a free body diagram. So this is the old way. keep in mind, you could tune out if you want. Here's the old method over here. Okay, and this here's your new method, which is much quicker. All right, let's do a free body diagram. So you have your free body diagram of the box. Remember that FA is over here. We have the normal force, and we have gravity, and we know the acceleration is this way. Okay, so let's do our F net equation. F net equals ma, and that's equal to FA. There's no FF because there is no friction. All right, let's plug it in. 10a is equal to 20, and then we have the acceleration, I believe, which is 2. Yes. So acceleration is 2 meters per second squared. Now that you have your acceleration, let's figure out the final velocity. I'm going to list my variables here. It started at rest. I'm trying to solve for velocity, the final velocity. My displacement is 8, and I'm ignoring time altogether. So let's use which formula here, the one that ignores time. So I'm going to use this one, 2AD. Let's plug everything in. 0 plus 2. You will notice that this technique does take longer to solve for, but I know a lot of you are used to doing it the old-fashioned way. Hopefully, though, you will get the same answer, which is kind of nice because you can actually double check your answer this way. All right, so there you have it. You have the old way and then the new way. On a final exam, let's say, basically, if there is a solution for energy, always choose the energy route. This type of question normally would be worth 2 marks because it's one side, actually 3, 1, and then for errors or, converting. So it'll be very quick. This is considered very quick and easy, and it'll only be worth 3 marks. But if you choose to do the old method, this method takes a lot more marks, but you only are going to have a maximum of 3 marks because it's only worth 3 marks because this is the fast way. All right, so bottom line is when we mark for physics, we always give you the marks for the shortest cut, the shortest or the best method. Okay? All right, let's do a quick summary of all the different energies that you have learned in this lesson. All right, so the general formula is F times displacement. Remember that any F net, Fg, Fa, friction, tension, anything. All right, so this is your general formula. Then you have the gravitational one, which is mgh. This is only reserved for things that you lift something up and it stays there and it's ready to fall back down and you need to calculate that. And the last one is the speed. Basically, how fast something is moving, you would need to know the kinetic energy.